So last time we discussed about representations, and I said that it's a good thing, it's quite handy thing for calculations to think of abstract elements of a group as matrices or some other thing, the permutation, so that calculations are easy. And we also saw certain matrix groups last time, and one of the matrix groups that I promised I would discuss today is SO3R, or simply SO3. And a couple of lectures ago we had seen that SO3 can be understood through its double cover, which is unit quaternions which have norm 1. You remember that, right? Whenever I have a unit quaternion, to that I can associate a map which is conjugation by Q inverse, conjugation by Q, so that is Q x Q inverse, that kind of map. And in understanding of rotations, this map is quite useful. So what's the purpose for today's lecture? Today we want to understand finite subgroups of SO3R. So you have group of rotations, there are so many axes, infinitely many axes, and there are infinitely many angles about which you can rotate. So thing is, in this infinite group, we want to find out number of finite subgroups. So before we do that, it's very clear to us that SO2 is a subgroup of SO3. So these are rotations in 2 dimensions. So I can always fix the axis. Say I am fixing the z axis and I am rotating. So that rotation is just a rotation in 2 dimensions, and therefore SO2 can be thought of as a subgroup of SO3. Rotations in 2 dimensions can be thought of as rotations in 3 dimensions as well. Yeah. And what are subgroups of this? What are finite subgroups of SO3R? So what is SO3R? It's not very hard to see that SO3R is actually same as S1, which is unit circle. So we want those complex numbers whose norm is 1, norm 1 complex numbers. So finite subgroups of S1, finite subgroups of circle, they are what? They are cyclic groups, finite cyclic groups. So therefore it's clear that finite cyclic groups are also subgroups of SO3R. But are these all? We want to know all finite subgroups of SO3R. And that's quite interesting problem which involves group action, and it heavily uses one-side formula for counting orbits that we had discussed a couple of lectures ago. Before we do that, let me mention that lots of finite subgroups of SO3, well, I should probably not be saying lots of, but essentially all. So they occur as groups of rotational symmetries of Platonic solids. I hope you remember what Platonic solids were. I had shown you certain three-dimensional objects. I'll show you again, and that's going to be your first job. The first job is going to be our understanding of groups of rotational symmetries of Platonic solids. In fact, in one case, in case of tetrahedron, we had seen this group. In fact, we had written this group and we had also made Cayley graph of this group in case of tetrahedron. Now let's recall Platonic solids. I'll show again this one. This has 20 faces. So F is 20. Number of vertices is 12 and number of edges is 30. And this is called, sorry, not Dodecahedron, Icosahedron. This one. Every face is a triangle. And then we have this thing which is dual to it. And this is called Dodecahedron. And how many faces does it have? It has 12 faces. And how many vertices it has? It has, let's count, 5 up, 5 down, 10, and then 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20 vertices and number of edges is 30. That is Dodecahedron. And this one is Octahedron. For this, number of faces is 8, octa. Number of vertices is 6. And number of edges is 12. I guess so. 1, 2, 3, 4. 4 up, 4 down, and 3 in the middle, 12. And then we have a cube which is dual to it. So cube has 6 faces and 8 vertices and 12 edges. 4 up, 4 bottom, 4 vertical. And this one, tetrahedron, where number of faces is 4, number of vertices is also 4, and number of edges is 6. 3 here, 3 vertical, 3 in the bottom, 6. And this is dual to itself. So what's the duality? Duality is between faces and vertices. Faces and vertices, that's duality. Here again, faces and vertices. And number of edges is equal. Number of edges is equal. And this is dual to itself. So for example, I can take this. I can consider middle of the face, middle of this face, and opposite face I hold like this, and then I hold it like this. So here the vertex is, you see, if I rotate about this axis, this is order 4 rotation. So I can rotate by 90 degree, 90 degree, 90 degree, 90 degree 4 times, I am back, and similarly here order 4 rotation 90 degree each. So the midpoint of the face is acting as midpoint of faces I am taking and joining them, opposite ones, and those are acting as axis. So this is face vertex duality, and that's how we call them dual. And now the question is how they are interesting in determining subgroups of S3. So Platonic solids and subgroups of SO3R. For that, let's first determine what are the groups of symmetries of these objects. And it's not very hard, everything is just about observation and putting in the right mathematical language. So we do that, and after that we are going to learn how can we determine all subgroups of SO3 in terms of Platonic solids. So let's take this one, this tetrahedron. Now what are all the symmetries? In fact, we wrote all the symmetries in terms of permutations, in terms of even permutations that we have already done a couple of lectures ago, where I said 1, 3 and then 2, 4, that kind of thing, and then 2, 3, 4, those order 3 and order 2 elements in a 4. Nevertheless, let's have a look at it again. So first job is to identify order 2 elements in the symmetry group. So how do you find order 2 elements in this? So here I take midpoint of edge and opposite side, right? I am holding it from the midpoint of this edge, and when I hold it, naturally the other side, my thumb is also on the midpoint of opposite edge. And now I can rotate by 180 degree. So if I rotate by 180 degree, I am like this, back to the similar kind of symmetric motion. This is symmetric rotation. So here is order 2 element in this. So order 2 element is, let me call it S. Order 2 element, and which is obtained by taking midpoints of edges as axis, midpoints of the opposite edges. Now what else is very natural order which occurs here in the group of this, the group of symmetry of this? Well, it's a triangle, so there has to be order 3 element. Naturally, which one? I take vertex and opposite face, midpoint of the opposite face I have, and then I simply rotate. I rotate by 2 pi by 3, 120 degree each time, and that's how I get order 3 element in this. I am just rotating with that as an axis, right? I am just rotating that as an axis. So here is T, which is order 3 element. And how do I get that order 3 element? So I take a vertex and I join it with midpoint of opposite face, and that's how I get order 3 element. What else? What if I compose two? What if I compose these two? What would happen? And that's going to be interesting. So I take first I rotate like this, and then I take midpoints and then rotate again. What is it going to be? That's interesting, and for this let's try to do a computation. Although what you can do, one way to see it is, so question is, what is ST, right? So one way is to actually do the experiment and realize what is ST, what is the order of ST. Or the other way, as we did some lectures ago, so order 2 element would be something like 1, 3, 2, 4, something like this. And what is T? T, let's say T is, so I am writing S here, so T, say for example 2, 3, 4. Let's compute what it is. So this is the edge joining, so this is the edge which is joining vertex 1 with 3, and other is vertex 2 and 4, and here the vertex 1 is having one end of the axis, and midpoint of the face 2, 3, 4 is having midpoint of the other point of that same axis. So what happens to 1? Here nothing happens, here nothing happens, and here 1 goes to 3. 1 goes to 3. What happens to 3? 3 goes to 4, and 4 goes to 2, and that's all. So 3 eventually goes to 2. What happens to 2? 2 goes to 3, and 3 goes to 1. So this is over. And what about 4? 4 goes to 2, and 2 comes back to 4. So this is it. So order is 3. Order is 3. So when you actually compose like this, order is 3. So you should be realizing that therefore ST is actually rotation, and this time this the vertex is 4th vertex. So this is a different vertex about which you are having this rotation. So one end of this is vertex 4, and you are having other end of the axis as midpoint of phase 2, 3, 4. So whatever is that, phase 2, 3, 4. Oh no, here in this case 1, 3, 2. In this case it's a phase 1, 3, 2, that phase. Yeah. So ST has order 3. So now I have group, consider the group G, which is generated by 2 elements S and T, such that square of S is 1. These are relations, remember, generators and relations. T cube is 1 and ST cube is 1. And by doing all this, what we have obtained is actually a homomorphism from this group to the group of rotations of tetrahedron. So here is this homomorphism, and it's a surjective homomorphism. Surjective because we have observed all possible symmetries in this. So that's how we are claiming it to be surjective. And what's the order of this? So observe by some work that order of G is 12 and the symmetries of tetrahedron, that order is also 12 and I have this surjection. So this has to be isomorphism. So what we have is that rotations of tetrahedron, the group is this, and it's not hard to see that this group is actually A4. The group is A4. You can actually, in longhand, you can do some calculations and obtain that this group is A4. You just have to observe these relations and these this kind of relations on these two generators. So tetrahedron symmetry is group A4. Let's see few more. Let me take my favorite one, icosahedron. What to pick first? Let's see, take vertices. If I take vertices and rotate, how much is the angle which is admissible for symmetry? You can see 5. So here is an element of order 5. Before that, let's see element of order 2. So again, the element of order 2 is obtained via midpoint of edges. So this is what you say, order 2 element. So order 2 element is present there. What about order 3 elements? Since triangles are there, midpoints of triangles, you rotate by 2 pi by 3, and that's what is going to give me element of order 3. So I take midpoints of faces, these triangles, and this is order 3 element. So how many order 2 elements are here? So there are total of 30 edges. There are 15 pairs of edges, right? So since 15 pairs of edges are there, I have 15 of these. So one is this position, other is that position. 15 of them. And order 3 elements, how many order 3 elements will be there? Again, there are 20 faces. So I will have one identity position. So there are a total 10 possible choices, and each thing is giving you 2 non-identity rotations. So what you have is 20 of them. What about ST? Again the same question. What is the order of ST? So for that, maybe you have to do some certain experiment. You make your own icosahedron and try to do some experiment, and what I can tell you is that ST to the power 5 is 1. So ST is of order 5, and that order 5 element is actually obtained like this by taking vertices. So this is obtained by taking midpoints of, or not midpoints, but taking opposite vertices. So when you take opposite vertices, you get order 5 element. And again, you can think of this group which is generated by 2 elements S and T, and the relations are x square is 1, t cube is 1, and st to the power 5 is 1. this group. And this group, it's not hard to see, some work is required, that this is actually A5. So group generated by this is A5. So from here to groups of rotations of icosahedron, you have again surjective map, and you know what this symbol S does? It corresponds to the midpoint of edges rotation, and similarly T corresponds to midpoints of faces rotation, that kind of rotation. And here it's again not very difficult to see that order of this is 60. So here actually if you look at order 3 elements, then they are 20, and order 5 elements, they are 24, because there are 6 options, there are 12 vertices, so there are 6 options, 6, and each pair of vertex, when you take as axis antipodal ones, opposite ones, then you get 4 non-identity positions. So 6 into 4, there are 24, and then there is one order 1 element which is identity. So there is a total of 20 plus 15, 35, 35 plus 1, 36, total of 60. So group of rotations of icosahedron has size 60, and if you look at these generators, and this is surjective map, these generators again have again generate a group which is of order 60. So here is an isomorphism. So A5 is group of symmetries of this object, which is icosahedron. Now for this dodecahedron is the same thing. It's all about vertex and face duality. So rather than saying all this, I'll write face, in place of face I'll write vertex here, in place of vertex which I'll write face here, and that's all. And so for dodecahedron as well, I get same symmetry group, which is A5. Now let us look at cube or octahedron, same thing. Let's take this cube. So what would be symmetries here? So first of all, order 2 element, and order 2 element is again obtained as midpoints of edges. So I take midpoint of edge, opposite edge, take the midpoint, and I get order 2 element, the same every time. And what if I take opposite vertices? So T, so order 2 element by taking midpoints of opposite edges, and T, which is order 2 element, sorry, order 3 element, I can obtain by considering opposite mid, or rather so opposite vertices. Yeah, you can see from here, so from top if I look at, there are 3 edges which are going, so just rotate these edges among themselves, and that's how you will get order 3 element. And now the question is, what is ST? So again, you can actually do experiment. If you want, you can label them so that you remember what is identity position. So if you do order 2 element, if you do this, and after that you do this, what actually you obtain is order 4 element. So ST to the power 4 is actually 1, and ST is obtained by considering opposite faces, rather midpoints of them. midpoints of opposite faces you take, and that's how you get st to the power 4. And again you consider the group which is on 2 generators S and T, for which relations are S square is 1, T cube is 1, and St to the power 4 is 1. And from here to group of rotations of cube, you give a map. So it's not very difficult to realize here that groups of rotations of cube has how many elements? Let's count it. So here how many pairs of edges are there? There are 12 edges. So 6 elements you will get this way, right? And here order 3 elements, you will get 2 times pairs of opposite vertices. So there are 8 vertices. So you will get 4 pairs, and each pair is going to give 2. So you get 4 into 2, 6 of them. And what about midpoints of faces? So how many faces are there? So you have 3 pairs, so 3 pairs of faces, and each face rotation is going to give you 3. 1, 2, 3, 4, it's 9. Please wait a minute, sorry, some editing will be required. I have written something wrong. Mohan, some editing will be required here.
You can erase and restart from the post.
Yeah. I'm doing this. So here in this cube, let's count how many order 2 elements are there, how many order 3 elements are there, and how many order 4 elements are there. So for order 2 elements, I'll see how many different edges are there. So there are total of 12 edges. So there are total 12 by 2, 6 pairs. So there are 6 elements of order 2. What about order 3 elements? So when I do order 3 elements, I am considering opposite vertices, and in each rotation I am getting 2 non-trivial, 2 non-identity positions. So I will multiply with, not with 3 but with 2. And how many pairs of opposite vertices are there? So there are total of 8 vertices. 1, 2, 3, 4, 4 up, 4 down. So I will get total of 4, 4 into 2 is 8. And what about opposite faces? So how many opposite faces are there? There are 3 pairs. And each of them is going to give me 3 different 3 non-identity positions. So 3 into 3, 9. And then you have 1 identity element. So how much is this? This is 24. So size of rotation group of cube is therefore 24, and it's not hard to see that this is also of order 24, and in fact this is S4, permutation group on 4 letters. And then again this surjective map becomes isomorphism as in earlier cases. So for cube the group of rotational symmetries is S4, and again by duality for octahedron as well, I have group of rotational symmetries which is same as S4. So what we did in this lecture today, we just saw all possibilities of groups of rotational symmetries of all these Platonic solids, and as you recall, I had already proved that there are only 5 Platonic solids, and these are right in front. And observation is that each of these objects can be put inside a sphere. Each Platonic solid can be put inside sphere. Say a unit sphere or whatever is the radius of these objects inside a sphere. And that is going to help us in determining what are all finite subgroups of SO3. So in next lecture we are going to see all that. It's quite a fun, it's very interesting application of group actions. See you next time.